Hello, everyone who is joining us watching the recording online. This week we are discussing Chapter 6, Sections 6.1, 6.2, 6.3, and 6.6. Does that sound about right? Cool. Is it okay with you if we just start at the beginning, 6.1, and kind of work our way through? Okay, so let's start with 6.1. So 6.1 is analyzing antiderivatives graphically and numerically. And you guys already spoke about antiderivatives, I think. But this kind of gets like a little bit more into like the detail of that. And I personally think that 6.1 is the hardest of all of these sections because it's really tough to like link what's going on with like an antiderivative to like what's going on in a graph. So why don't we start with question 6? I think is a good like overview question. Oh, and this is on page 294. Okay, so figure 6.6 shows the derivative g prime. If g of 0 equals 0, then graph g. Give xy coordinates of all of the local minima and maxima. Where would we start with this problem? Any ideas? I would start with what I know. So I know that g of 0 equals 0. When I see this, what do I think of, this phrase? It means that I'm, oh yeah, no problem. This phrase kind of is going to make me want to think of using Fundamental Theorem of Calculus. Because I know that, for instance, I have a curve that I can find the area under, and I have this. So I know that g of, g of x minus g of 0 is equal to, from 0 to x, g prime dx. Right? So seeing g of 0 is going to kind of tip me off that I'm going to be thinking about using the Fundamental Theorem of Calculus, which is in line with what we've been doing. Next, what else do I know? This kind of refers back a little bit back to like what it means to like be a derivative. So I know that when g prime is positive, it means that g is increasing, or the derivative of g is positive. So I'm going to do, and I know when g prime is negative, that g is decreasing. Okay. So those are two things that I know. I also know things about critical points. I know that critical points exist where g prime is equal to 0. So where are the x values that are going to be like where my critical points are at? Well, if I look at this graph, I have, 4 and 6 exactly. So I have my critical points at x is equal to 4 and x is equal to 6. Now the question is, what are these? Which we can get on figuring out. Give me a sec, just gonna make sure that we have, yeah. Okay, so that's all I have for like starting off with like what we know. And then I'm gonna quick write down what we want, and then we can get to solving the problem. We want ordered pairs to graph. Okay, so given that g is we want to find what g of x is. For g of 1, g of 2, we want to find all of these. So that's what we want from this problem. So we're going to start off by finding what the critical points are. And the way that we're going to do that is we're going to take a look at the graph, which looks something like this. Something like that. And here's 4, and here is 6. And what we're going to do is basically we're going to do the exact same thing we were doing when we were thinking about critical points. We are going to draw a line and say here is 4 and here is 6. And we know that these are our critical points. Before 4 in this area, this is g prime, right? So our derivative is going to be positive, because g prime is above 0 for this whole period of time, and then it's below 0 for this period of time. So 4 is a maximum. And we don't have enough information to tell whether 6 is a minimum or if it's like just continuing on down. But that's not important as to like what the question is going on right now. So we know that 4 is going to be the maximum. Okay, so we have this information. I'm going to clean this up a little bit. We know it's going to have x equals 4. Know that those are where the critical points are at. Okay, and we know that we should be thinking about the fundamental theorem. So where are we going to go from here? We have this graph. We have g is equal to 0, or g of 0 is equal to 0, and we have the fundamental theorem. Well, we're going to use that fundamental theorem to find g of 1. So we're going to start off with saying this, we know this to be true because it's the fundamental theorem. G of 1 minus g of 0 is equal to the integral from 0 to 1 of g prime. Okay. Now, we do know that this is going to be the area under the curve. Come on, write that down. Correct? So if we look, we can see that half a box is the area under the curve from 0 to 1. So we know that this is equal to 1/2. So I'm going to rewrite it like this because I know that g of 0 is equal to 0. So g of 1 minus 0 is going to be equal to 1/2. So g of 1 equals 1/2. Okay. So I am going to start writing this down in a table so that I can track down. So here is the interval. Get a straight. Okay. So there's the interval. Here is going to be the area under that curve. And here is, so this is going to be specifically from A to B. And then this is going to be the total area. All right. And this is g prime of x dx. Okay, so here we know from the interval from 0 to 1, the area under the curve is going to be 1/2. And from this is from 0 to b, we'll say, right? Because b is as far as we're going. So from 0 to b, it's going to be 1/2, because at this point in time, b is equal to 1. This is in the form a, b. Okay, does this table make sense? What I'm doing? I'm just trying to like set it up in a way that makes it easy to see what's happening. Okay, so then what we're going to do is we're going to do this all the way down. Okay. So we know that these are the individual intervals we're going at. We're checking out each individual box as we go, and we're going to be using the same method. Okay, let me clean up this a little bit. Okay, so g of 2 minus g of 1 is going to be equal to, oh, we also need, oof, can't forget this, x and g of x. So we need another table basically telling me what the ordered pairs are. So that we'll for sure remember what's going actually on. Cool. Okay. So we know that g of 0 is equal to 0. G of 1 is going to be equal to 1/2. G of 2 is where we're at now, and we're going to fill out this whole table. 5, 6. I don't know why. Okay. So we need to fill out both of these tables if we're going to figure out what the answer is going to be. So g of 2 minus g of 1 is equal to the integral from 1 to 2 of g of x dx, correct? So we know that g of 1 is equal to 1/2, so g of 2 minus 1/2 is equal to, and if we look under here from 1 to 2, there's one box that's 1 by 1. So the area of that box is going to be 1. That's going to be equal to 1. So g of 2 is equal to 1. We're going to add 1/2 plus 1/2. G of 2 is equal to 3/2. I'm going to write that here. This, I'm going to say this is the area under this is 1, because that's what my derivative is equal to. And so the total area is going to be 1/2 plus 1, or 3/2. Okay? All right. So I'm going to erase this again, give myself some space to do this a couple more times. Oh, shoot. Okay. All right. So g of 3 minus g of 2 is equal to the integral from 2 to 3 of g prime of x dx. I'm also going to write down that g of 4 minus g of 3 is equal to the integral from 3 to 4 g prime of x. So we know that both of these are true. We said that 2 is going to be 3/2, so this is g of 3 minus 3 over 2 is equal to, if we look under here, the area is going to be 1, so this is going to be 1. So g of 3 is going to be equal to 2 over 2 plus 3 over 2, so that's going to be 5 over 2. So I'm going to put that in here, 5 over 2. This total area is also going to be 5 over 2, I believe. Okay. So then we're going to bring this up to here and say that g of 4 minus 5 over 2 is equal to, and then here again we have an area under the curve of 1/2 from 3 to 4. So this is going to be 1/2 plus 5 over 2 plus 5 over 2. G of 4 is going to be equal to 6 over 2, or 3. So here we have 3. Okay. Then we're going to continue going on between 4 and 5. So we have g of 5 minus g of 4 is equal to the derivative, or excuse me, the integral from 4 to 5 of g prime of x dx. And this is going to be a little bit different because we know that we have g of 5 minus 3. And this is equal to negative 1/2 because now we have a negative integral. So we're going to add 3 to both sides again. But g of 5 is going to equal 5 over 2. Okay. Oh, and give me a sec to erase this. Okay. So then we're going to have g of 6 minus g of 5 is equal to, from 5 to 6, g prime of x dx. This is going to be g of 6 minus 5 over 2 is equal to negative 1/2. Add 5 over 2 to each side. So g of 6 equals 2, or 4 over 2. Okay. So it's 1/2 also. So yeah. So this is kind of just like this table over here to the left was helping us, like, if that's not an eraser, come on, helping us keep track of things. But now that we have our list of in the table to the right of all of the ordered pairs that we need, remember that's what we wanted. We need to graph this, I believe. So yeah, if g of 0 equals 0, graph g. So we're trying to graph g, and we have all of the ordered pairs of x and g of x. So now we can actually do the graphing. Here, I'm just going to erase this all, and I'll rewrite the table. So we have x, g of x, 0, 0, 1, 1/2, 2, 3, 4, 6. All right, let me quick look at this. This is 2, 5 over 2, 3, 5 over 2, and 3 over 2. So let's draw ourselves a graph. So here's going to be 3. That here is going to be 3 over 2. Which would make this 2, 5 over 2, 1, 1 over 2. And then here we're going to just do 1, 2, 3, 4, 5, and 6. So what we're going to do is plot these different points. 0, 0, 1, 1/2, 2, 3 over 2, 3, 5 over 2, 4, 3, 5, 5 over 2, and 6, 2. The graph looks something like this. Cool. So this is the graph of g of x. And we got all of that from having an initial value and the graph for g prime of x. We know from our critical points that 4 is a maximum, or x equals 4. And now we know that the ordered pair for that is going to be 4, 3. So this is our maximum. So this also makes sense because 3 is the largest number here. So when we graph it out, 3 is on top. So it looks like a maximum. It fits with everything that we've been working to up to this point. So it seems that we did everything right. Were there any questions about how this happened?
So do you have to find the maximum and the minimum? Hello?
Okay.
Olivia, are you hearing me?
Let's try to do let's also do number 4. Oh, I can't hear you now.
Oh, I was asking if we... Hello?
Yes, I can hear you now.
Okay, I was asking if we had to find the maximum and the minimum first before we actually worked the rest of it out, or we could have just pulled it from the graph.
No, you totally could have pulled it from the graph. I was just trying to link to what you guys already knew about what a derivative is, because we knew that this was the derivative of the function, and where a derivative equals 0, that's a critical point. So I just wanted you to connect past weeks to this week.
Okay.
Yeah. Okay.
Can we do one of the ones with the line graph?
Like number 10?
Yeah, 10.
Okay. All right, let's do 10. So this is still on page 294. What we have is we have this graph. So this is 1, this is -1, this is 1, and it goes like this. Come on. Okay, so that's a straight line, theoretically, and this is f of x. So we want to graph f of x, capital F, in 2 cases, where f of 0 equals 0 and where f of 1 equals, or f of 0, excuse me, equals 1. Okay, so my first thing when looking at this and knowing that they wanted me to go from this graph to the graph of the antiderivative, I thought of what these equations would look like in algebraic form. Because for me, it's very difficult to say okay, so this graph needs to be going up in this spot and going down in this spot. So I thought this would be a graph y is equal, or f of x. Let's do it like that. F of x is equal to x, because this is a line with a positive slope. Then I thought, if I were to find the antiderivative of just plain x, it would be 1/2 x squared. Because I'm going from this to this. If I were to take the derivative, I'd end up here. So we have this like this. So I know that I'm looking for parabola. That's not how you spell parabola. Okay, now that I know that, where is my critical point going to be? I know that I have a parabola that is either going to look like this or like this, and I need to know if I have a maximum or a minimum. Well, what I'm going to do is I'm going to say, I'm going to pretend like this is like a derivative graph, so I'm going to write myself a number line that goes from 0, here's 1, here's 2. I know 1 is going to be my critical point, because that's where the graph is equal to 0. Before that, it's negative. And then after that, it's positive. So this is negative, and this is positive. So it looks like I have a minimum. So let me quick go through. That's not what my graph looks like. This is what my graph looks like, and that is at 1. Okay. So min at x equals 1. Cool. Now that I know that, and I know that I have a parabola, here is this. And of course you could like, just like, okay, yeah, let me solve this problem like the first way first, and then we can talk about like different ways to approach it. Okay. So then what we're gonna do is, we have it like this. Here we have 1. We know that's where our minimum is going to be. Then it's a question of if where do I start? Like, what is my y-intercept going to be? Well, fortunately, that is given to us by these handy-dandy starting places. So I'm going to do these in 2 different colors. So for f of 0 is equal to 0, what that is telling me is that if I were to do x f of x, I would have 0, 0 as one of my points, correct? So I am going to start right there. And I'm going to go down and up. So there's my parabola. My minimum is at x equals 1. On the other hand, if I have f of x is equal to, or f of 0 is equal to 1, then I have a list of points that looks like this, 0 and 1. So I'm going to start up here at 1. I'm going to come down. That minimum isn't quite in the right place. Again, my minimum at x equals 1. If you wanted to be more precise, this graph, you could actually figure out like points after this, like for x equals 1, what is this point going to be? What is x equals 2 going to look like? I don't think that's like necessary for this problem, like for finding like what answer that they want you to find, because this is basically like the format of, this is like what the answer should look like here. But the reason you can do this is because you can actually get an equation from here. You know your y-intercept, you know your slope. You can actually get a f of x is equal to x minus 1, I think. Right? Yeah. That's a 1. So then you could take the antiderivative of this, yada, yada, yada. Okay. Feeling a little bit better about this? Cool. All right. Let's move on to 6.2 before. Okay. So here we have antiderivatives and the indefinite integral, and this is like my absolute favorite stuff about integration. I love indefinite integrals. I don't know why. So all right. So we're going to do 8, 10, and 12 to start off with. And what we're going to do is ask, is this a number or a family of functions? What do you think for number 8?
Number 8 is a number.
Yep. Number 10?
A family.
Mm-hmm. And 12?
A number.
Yep. And the reason that is because 8 and 12 are definite integrals.
I did get confused on 13 because they put both of them in there.
Mm-hmm.
But I eventually figured out that it was a number instead.
What was that? 13?
No, I'm saying that number 13 was kind of confusing because they had both of them in there.
Yes.
But then in the end, I end up figuring out that it was a number.
Okay. Okay. I would assume that that's a family.
Not an. Yes, a family, not a number. Yeah. Sorry. Yeah.
13 is also a family. And the reason these are families are because they have an indefinite integral. Cool. Okay. So you got that done, Pat. Let's do a couple of these antiderivatives, and then let's find a couple indefinite integrals. So, wait, you guys do, let's do evens. So let's do 16. Let's do 14, 16, 22. 32. Let's do 34. Okay. Would you like to just like take a second to go through and try to do these, or do you want me to just go ahead?
Can I just have a second?
Yeah, for sure.
Okay.
Oh, cool. You ready? All right, what do you got for me?
For 14, I did one of them wrong. Wrong question. I have 5t squared over 2.
Okie dokies. Yep, that should be right.
16 is t cubed over 3 plus t squared over 2. I did the wrong one for 22, so that one you're just gonna have to put up.
Let's do 32 then.
32 is e to the z plus 3x.
Oh, 3z.
3c.
It's just
3c, yes. Z.
xz. What's really the difference?
Yeah.
And then 34.
34 had a hard time.
Yeah. This one's a little rough.
Yeah, I got the others and then I'm like, what?
What do you think it is? Is it the x to the 0 that's throwing you off?
X to the 0.
Yeah, this is the term.
Oh, okay, yeah, because that one, yeah. If you do you leave it like that, or do you just change them around to be like x to the -1?
Okay, when I do these, I say that g of x is equal to x to the -1.
That's what it was.
X to the -2 plus x to the -3 because it helps me. But this is actually easier to leave in the form of 1 over x.
Okay.
Because this is not going to be taken up here as x to the 0.
Okay.
That's not going to happen.
Yeah, I got a little bit thrown off with that one. So
yeah.
Would it be like just 1 over x squared, or
no,
it's 2 over x squared?
This is a dirty rotten trick.
Okay.
Remember, if we take the derivative of this, what do we get? We get 1 over x.
Yeah.
So
I didn't even see that.
Yeah, I know. So I was doing this problem and I was like, wait, what do I do? And then I was like, oh no, natural log. Okay, so yes, this is going to be the natural log of x because this is so 1 over x is harder to write as 1 to the x to the -1, and that is because this is more recognizable as the derivative of natural log.
Right. If it was to another power, it would have been different.
Yeah.
Okay. No, I see. I didn't even see it.
Yeah. No, it's fine. That one's a rough one. A rough term. Do you have the rest of this?
No, I didn't do the rest of it. I stopped because I was like, wait, this looks weird.
Yes. Okay. So what we're going to do for the rest of this one then is we're going to say, again, we're going to be doing essentially the same thing, but we're going to be adding.
Mm-hmm.
So we're going to say, okay. So I can take the antiderivative of this and put it up here plus the antiderivative of this, right? That's how this works. So I need to find the antiderivative of x to the -2. Well, the way that I do that is I add 1, so it'll be x to the negative 2 plus 1 over whatever this number is, which in this case is negative 1. So it'll be x to the negative 1, but it'll be negative x to the negative 1. So instead of having a plus sign here, I'm going to have a minus. So minus x to the negative 1. And then I'm going to do the same thing here. I have x to the negative 3 plus 1 over negative 3 plus 1. So I'm going to have x to the negative 2 divided by negative 2. So again, minus 1/2 x to the negative 2. So you can write it either as this or as this. They're the same thing.
So even though you didn't change the first part of it into the form x to the negative 1, you were still able to do that for the others?
Yes. Okay. Because if I were to take, so if I take the derivative of ln of x, that equals 1 over x, right?
Yeah.
But if I take the derivative of x to the negative 3, what's that going to be? It's going to be negative 3x to the negative 4.
No, to the negative 2?
Well, it's going down.
Okay, down, yes.
So even though these numbers appear to be getting bigger, what they're actually doing, they're becoming more and more negative.
Yeah.
So that's what happens when you take the derivative of stuff with negative numbers. So taking more and more derivatives gets this number up here to be very small. So if I'm taking the antiderivative, it's going to be raising this number. So this goes from a negative 3 to a negative 2. Just like if I had a 3, it would, like an x to the 3, it would go to x to the 4 in the antiderivative. Right?
Yes.
Okay, so that's why those numbers appear to be getting bigger. And the only reason 1 over x is like this is that it's the special case of the ln of x. Because if I tried to follow that same rule, I would end up with x to the negative 1 plus 1 over negative 1 plus 1, which would be x to the 0 over 0. What am I going to do with that?
Exactly.
Typically, if something happens like this, it means you're doing something wrong. And it's just like a good indicator that maybe you should go back and reevaluate some things. Okay, so we need to do 22.
Okay.
All right, so we found those antiderivatives. 22 is going to be h of y is equal to 3y squared minus y cubed. So our h, capital H of y, is going to be equal to, it's going to be 3 times, and then this, the antiderivative of this is going to be 1 over 3 y to the 3 minus, and then the antiderivative of this is going to be 1 over 4 y to the 4. I'm going to simplify this. H of y is equal to, these are going to cancel, y 3 minus 1/4 y to the 4. So that's the antiderivative. And you can tell something is an antiderivative if they just go from a lowercase letter to a capital letter. That's kind of like the mark of an antiderivative. So yeah, there are some antiderivatives for you. Now let's do some indefinite integrals. Let's do 62, and let's do 72. Do you want to try these on your own too?
Oh, we can do them together.
Cool. Okay, so we're going to start with the integral from, or no integral from anywhere. It's just the integral of e to the 2t dt. Okay. So, well, we can't use the fundamental theorem of calculus, so we're going to use antiderivatives to solve this. We're going to take the antiderivative of this, which would be 1/2
Yep.
e to the 2t. And then we're going to add c. So we have a family of functions. And that's all there is to this one. The difference between finding an antiderivative and an indefinite integral is this c here. So now that the c is there, we're done. Cool. 72. We're going to do cos theta d theta. This is we're gonna find the antiderivative of it, which is going to be sine theta.
Yep.
Plus c. Ta-da! So these are our indefinite integrals. Did they talk to you about the why Did they talk to you about solving? Let's just move on to 6.3 because this will be relevant in 6.3. Yes, this will be very relevant in 6.3. Okay. So here we have 6.3. So now we're using the fundamental theorem of calculus to find definite integrals. Okay. So let's start with 2. So we have an integral from 1 to 3 of 5 dx. So first thing we're going to do, what do you think? Well, let's consider this for an instance. Can we solve it in the traditional method that we have of having a starting value? What are we trying to solve this for? We don't have an area under the curve. What are we going to do to solve this? We're going to have to use our antiderivative skills. So we take an antiderivative of this. It's going to be 5x. Plus c, right? But this is on a scale from 1 to 3 because these numbers still matter. So basically what I did is I, 1, took the indefinite, and then 2, applied the range. So here's our indefinite integral, and here's our range. So what are we going to do with this? Well, we know this is from x is equal, so this is equal to x, and this is equal to x, right? So what we're going to do is we're going to end up subbing these in. We're going to say we know that f of 3 minus f of 1 is equal to, from 1 to 3, f of x dx. We're going to say this is equal to 5. So here's our antiderivative of 3 and of 1. Correct?
Yes.
Cool. So here's our antiderivative. And what we're going to do is we're going to say 5 times 3 plus c minus the quantity 5 times 1 plus c. So is equal to from 3 to 1 f of x dx. We want to solve for this. Okay. Basically what we're going to do is we're just going to simplify this out. We're going to say this is 15 plus c minus 5, and I'm distributing this negative sign to both of these. This is going to be minus 5 minus c is equal to this. So these c's are going to cancel, and it's going to be 15 minus 5, which is 10. And that's our answer. Are we cool with this?
Yes.
Awesome. The really cool thing for me is that C is still going to be there. When you're solving for definite integrals, typically you don't write that C down because you know it's a definite integral and it's going to go away. When I started doing this, I would oftentimes forget the C when I was doing indefinite integrals, and that what really helped me was to write it out always. So it is up to you. It's a time commitment to write down C every time, but it does, it's a helpful reminder that that is there. So that C is there in a definite integral, but oftentimes people don't write it like that. Okay, let's try another one. What am I going to do with this? First thing I would do is simplify it into something that's more manageable. Because I know that there's a plus sign in here and I can add integrals, what I'm going to change this into is from 0 to 2, 12x squared plus the integral dx plus the integral from 0 to 2 of 1 dx, because that's more manageable. Then I'm going to turn this into, simplify it again, I'm going to put this 12 on the outside because I don't even want to think about it right now. And then I have x squared dx. Okay. So then we move on to our next step, which is going to be finding the antiderivative of the stuff in the middle. So we have 12 times, we have 1 over 3 x cubed from 0 to 2. And then we have this is going to be x from 0 to 2. So we're going to continue on in this pattern. We have 12 times 1 over 3 x, or excuse me, not x. This is going to be 2 to the third minus 1 over 3 to, or 0 to the third plus 2 minus 0. Simplify it further. We know that that's going to equal 0. We know that that is 0. So we're going to end up with 12 times 1 over 3 times 8 plus 2. I know that 12 times 1 over 3, this is basically all just being multiplied together now. There's no other terms. And we could have distributed the 12 up here as well, but I just kind of had it separate because I separated it all the way back up here. So this is going to end up being 4 times 8 plus 2, or 32 plus 2. So this is going to be 34. And so we have a definite integral that gives us a number. Thoughts, comments, concerns?
Okay, we didn't do the integration by part. I know what you're showing me. I understand the whole thing. Mm-hmm. But in this section that we did, we hadn't practiced this yet.
Oh.
But it's the same. I know that. But so can you also write it the other way too?
What's the other way?
You said with the plus, you just separated it, right? Could you have done it as one whole thing?
I mean, it is
harder. Yeah.
So
now I understand it's fine. You don't really have to do it, but I know that you could have also done the other way, correct?
So I mean, it's it is the same thing if you do it like this. Because the only thing you're doing is not explicitly moving over here. It's the same principle, and you're following the same pattern. You're just taking this out and moving it to the end.
Okay.
So the way that you would do that is you'd have 12x, or 12 over 3x cubed plus x from 0 to 2. Is that what you're looking for?
Yeah, and that's fine. Like, I understand what you did. I didn't have a problem with it, but maybe for somebody else, they might get lost.
Yeah, no problem. I always find it easier to like separate them out into like different chunks by these like addition signs, because that is actually what you're doing here. So this is like skipping this step and skipping this step and like just adding them together right here.
Okay.
So they're the same thing. It's just you're skipping a couple steps when you're doing this dark blue over here.
Okay.
So yeah. Okay. All right. Let's do a couple more, and then let's quick do some from 6.6.
Okay.
So let's do. Is there a question that you have about how to do one of these? Because we can talk about one that you were having some trouble with.
Not in this section. I don't think it was. I think it's in 6.6 that I.
All right, let's talk about 6.6 then.
Okay.
All right. Ooh, U substitution. Gotta love this stuff. Or do they do it with W in here, don't they?
Yeah, they have a lot of X and Y's. Oh yeah, in the book, yes, they do it with W and U.
I learned it as U sub, like U substitution as always a U. So it like shocked me when I read this book and it was like W, and I was like, ooh, okay. Okay, let's do 6.
Okay.
So this is on page 320. We have this integral. It's an indefinite integral. We have 2x squared plus 1 dx. So what do you think our substitution is going to be for?
For x squared plus 1?
Yep. Okay, and so the way that I learned this, now this isn't like technically like mathematically correct, but consider if you were to take the derivative of this with respect to x, you would end up with du dx is equal to 2x, right? So multiply both sides by x, or dx, you have du is equal to 2x dx. So is that really how this term works? Is it really a fraction? It's not, but this is a good way of visualizing like how this works out like it does. So what we're going to do is we're going to say that here is our u. So we have u to the 5th, and then we have 2x dx, which is equal to du. So now we have du. So the integral of u to the 5th du, cool. We can work with this. So we're going to find the antiderivative, which is going to be 1 over 6 u to the 6. And then we're going to substitute u back in. So u comes back. So it's 1 over 6 times squared plus 1 to the 6. And that's, plus c. Because there's also a plus c here. So that's actually that answer. So once you get it down into this form, it gets easy to solve. The trick is getting it to that form, like finding out what u is going to be, what du is going to be. Does that work? Sometimes you have to play around with it a little bit. But yeah, so this is how the substitution kind of goes. What questions did you have about this section?
It was question 23. I think that's the one I think that was the only one I couldn't figure out.
Okay. That's application. That's application. Okay. Okay. So, give me a hot sec. Actually, why don't we just try to solve it? So let's first try u being y squared. That would mean du is equal to 2y dy, right?
Yes.
So if I were to go through and do this, it would be u that's not going to work. So basically the way that I solve these is by trying things, and so that didn't work. 1 plus y is not going to work. Do they have you solving by?
Can you break down 1 plus y, like do I don't know if that would work, but I think I tried it and I'm not sure.
That's a really good thought. So 1 plus y times 1 plus y. So this is going to be 1 plus y plus y plus y squared. So this is going to be y squared times 1 plus 2y plus y squared dy. You're right. This is how you solve it.
Really?
Yes. So it's going to be y squared plus 2y cubed plus y to the 4th. It's got to be this. Why would you even need u sub to solve this then? I don't even think you need u sub to solve this. There's nothing to substitute in. So what you're going to do is you're going to take it down and you're going to find antiderivatives for each one of these individually. And you're going to tack C on at the ends. So no substitution. So this is 1 over 3 y to the 3 plus 2 over 4 y to the 4 plus 1 over 5 y to the 5 plus c. Simplify this down, y over 3, or y to the cubed over 3 plus y 4 over 2 plus y to the 5 over 5 plus c. That's how you solve it. So this was kind of thrown in there to trip you up because what they wanted you to do is try to put this stuff in the interior as u. But basically, if you can't make it fit, like if this doesn't work, if your trial and error isn't yielding anything, then you have to try it another way. And that was a really good way of trying it. So good job.
Okay. I tried, but I'm like, there was nothing to substitute, and I was getting hung up on the question, so I just moved on to the other.
No, that is exactly how you tackle it, is you think about other different ways to solve the problem. So yeah.
Okay.
Cool. Yeah, that's basically it. I only have a couple minutes left. Do you have any questions?
No, that was it. That was the only question 6.6 that gave me a problem.
Cool.
The one in 6.1, you already took care of that one. So.
Oh, awesome. Cool.
So we're all set.
Awesome. Well, you have a great week.
You too.
Have a good one.
Okay, bye.
Bye.